Welcome to the first lecture related to the topic ordinary differential equations. In this video lecture, we will explain what are ordinary differential equations and why are them so important for engineers. So I'll start by understanding the name. What's the meaning of ordinary differential equation? Yeah. To start, let's see the meaning of equation. We all know what an equation is, but normally we think in this type of equations that are called algebraic. Algebraic equations have a solution x that normally it's a real number, okay? So when we talk about equations, normally we think in algebraic equations. Now, what we will see in this chapter is not the type of equations that are called differential. Why is that? Because there will be an unknown that it would be a function. So, for example, my equation, of course, will have an equal sign. That's why it's called an equation. But the unknown is going to be the function y of x. So this is an example of a differential equation. This is a differential equation where now the unknown, it's not anymore just a single value, but a whole function y of x. That's my unknown, okay? Now it's a function. So that's why they are called differential equations. Then later we will see why we call them ordinary. There will be another type called partial differential equations that will not be studied here in this course, and we will see the difference between these two, okay? So let's change now to the topic, to the definition. Here we have the definition of a differential equation. It says is an equation that contains the derivative of one or more functions with respect to one or more variables. Okay, so here we have to think that we have a function yx, okay? So this x is called the independent variable, okay? And y is called the dependent variable or the function, okay? Now, this is an example of differential equation. Y prime x plus yx equals x squared. Here, the unknown is the function yx. This is what we are looking for, okay? So this is much harder than an algebraic equation where the solution is just a number, because now the unknown is a whole function, okay? So this is very important. Now, here we have some different examples of differential equations. This first one here is a function u that depends on two different independent variables. So in this case, when we compute the derivative, we need to explicit the partial derivative with respect to which variable, because there are two different variables, t and x. Yeah. So here, this would be called a partial differential equation, because we are using a function that depends on two different variables. Instead, if we have a function that only depends on one variable, then we call it ordinary differential equation, okay? Here you have different notations for the same concept. The first partial derivative of u with respect to x can be written in these two different notations, but they just mean the same thing. And basically, in this course, we will only deal with ordinary differential equations. So we will only deal with equations where the function y depends only on one independent variable. Normally, we will think in time instead of calling it x. The independent variable is usually called t because we think in time domain problems. So you will see in the next slides that normally we use this notation. Okay? Now, very important here, the solution of an ordinary differential equation is a function. That's not completely true. I will add here that the solution of an ordinary differential equation is a family of functions. And we will see later on what do I mean with this. Okay? Now, this is a slide where the most important types of partial differential equations are shown. But as I said, in this course, we will concentrate in ordinary differential equations. So I will skip this slide. Now, this is very important. Now, I would like to emphasize that ordinary differential equations and also partial differential equations, they are very important for engineers, for example, because they model reality and they allow us to model what's going to happen without needing to go to a lab or to an experiment. Let me explain this with an example. Let's say we have a real problem we want to solve. Let's imagine this real problem is, for example, I want to design a parachute and I want it to be secure for a person to jump with that parachute and have a secure landing. Yeah. So this is my real problem, and I need to do some hypotheses, some assumptions, because real life is so complex. There are so many variables to take into account. It's almost impossible to make a model that takes into account everything. So we will always need to do some hypotheses, some assumptions, and derive what is called mathematical model. So, for example, for the parachute problem, it will make sense to make the assumption that, for example, if I'm jumping from the top floor, from a roof in a building, it could make sense to assume that I will fall vertically. So I could assume, for example, a one-dimensional problem in that case, because I'm just taking into account the vertical displacement. That could be an assumption, an hypothesis, quite close to reality, and that would allow me to derive a mathematical model which is simpler enough, but at the same time real enough. Yeah. So in this case, if I think in the parachute problem, of course I will need second Newton's law, force equals mass times acceleration, to derive the differential equation. As you will see, second Newton's law, Kirchhoff's law, they are, in fact, differential equations. We will see this in a few seconds. Okay, so now I have my differential equation that models that real problem, and I can try to solve it. I can do that analytically, as we will see in this course, or numerically. We will see some examples on how to solve the numerical equation, the differential equations numerically. Either way, you will get a solution of your mathematical model. And of course, if you did it numerically, in this step, you will have some error coming from that approach, from that approximated approach that comes always with numerical solving. But even when solving it analytically, you will also have some error because you did some assumptions from the real problem. Okay? So either way, when you have your solution from your mathematical model, you need to make predictions given by this model, and compare them with real life and compare them with reality. Once you contrast with reality and you validate your model, you make sure your model is making good predictions, then you can use this mathematical model to develop better the shape, the material of your parachute. So this loop that you have here is very important, and it's used a lot nowadays to design new things, to design new mechanical pieces, to design a new bridge, because it really allows to make predictions just using a computer with no need to experiment, just need to experiment to do some validation from time to time. But let's think in another example. You want to simulate or to model the frontal crash of a car. If you do that in a lab, you really need to construct a prototype and crash the car, and every time that's very, very costly. Instead, what you do is to construct a mathematical model in your computer. You simulate that frontal crash, you make predictions, and once you have your designed new bumper, then when you have the best design, then you do the experimental simulation, but very few of them. It's really make a difference in the cost of developing new products. Okay, so these are some examples that are modeled by differential equations. The first one is a very simple problem where we have a mass attached to a spring with a spring constant k, and here y is a function of time, okay? And y is the position with respect to equilibrium at time t, okay? So let's say that if this is the equilibrium position where y is equal to 0, then this function yt will tell us the position of the mass at each time t. Of course, when I take position and I compute the first derivative with respect to time, I get velocity. And when I compute the second derivative of position with respect to time, I get acceleration. So here, if we use Hooke's law, which tells that for a spring, the force is proportional and in the opposite direction of displacement, and second Newton's law, which is force equals mass times acceleration, we will get this differential equation we can see here. You see, mass times acceleration is the second derivative of position with respect to time equals the forces which are done here by the spring, which is minus k times y. So second Newton's law here is showing us that it's nothing more than a differential equation, because the unknown here is yt, the position at each time t, but the equation involves the second derivative, the acceleration. Now, if we want to solve this problem in real life, we need some extra condition. We really need to know the initial position of the mass and the initial velocity of the mass. It is not the same if I just let it go or if I really give to it an initial velocity. So the initial position and the initial velocity are important to really define a unique solution of the problem. This is going to be a very important concept. Okay? Now, another example I want to explain in detail is the parachute. We were talking about this example before. Here, let me go back here, for example, in this mass spring problem, we did not take into account, for example, friction. Yeah? We are assuming, there is an hypothesis that is done here, and it's that friction is not important in this case. And this would be a very good model for the initial time, for the initial movement of this mass. maybe the first seconds or the first minutes. It is a good model because it's simple and it really models reality in these first time steps. However, if I want to solve the problem of the parachute, the assumption of not including friction is not a good idea, because friction here is a very important part of the problem, because it's what is going to save my life. Friction is the force that is going to decelerate the person from falling down very fast. So here for the parachute problem, I need to include friction. Here what we are doing is including this friction force that is proportional to the velocity of falling down. We know that. The thing here is that this constant is quite complicated. It really depends on air density. It depends on the shape of the parachute, the geometry. It depends also on the material of the parachute. So it's really a quite complicated constant, but we know it's constant. So here I just simplified it by calling it K, okay? So we have friction here, which is K times V. And I'm using here the idea that it is falling in one dimension, okay? So here y is the unknown. Y depends on t, time, and y is the position. In this case, is the vertical distance to the ground, okay? So basically, it would be better to plot it like this, okay? So the ground is the zero level, and y is the position, vertical distance to the ground. Okay, so here again, we are using second Newton's law, but in this case, the forces come from the weight of the person and the friction, okay? So this should be a plus, of course, okay? They are opposite signs. So finally, we have that mass times acceleration. Remember that this is acceleration, the second derivative with respect to position, is equal to the forces that are the weight minus the friction. But again, this problem will have many different solutions if I don't fix some initial conditions on the problem. It is not the same to jump from the top floor of a building or to jump giving a different height. Okay, so I need to know the initial position where I'm jumping from, and I need to know the initial velocity. In this way, I can define a unique solution of the problem. But this is going to be a very important concept. If I only give an ordinary differential equation without any additional condition, the problem will have many different solutions. It will have a whole family of solutions. Now, let me introduce some important notation definitions. The first important definition is the order of a differential equation. This is very simple. The order is given by the highest derivative that is present in the equation. So for example, here, this is a first order differential equation because the highest derivative that appears is a first derivative. Here, for example, I have second partial derivative. So this is a second order partial differential equation. This one can be a little bit tricky. Okay, this one here. This power 4 is power 4. It's not the fourth derivative. So this is just the first order differential equation because the highest derivative that appears is first order. So in general, an ODE of order n with only one dependent variable, so let's say we have this function yt, the ordinary differential equation of order n can be written in this way. It can only appear the independent variable t, the function, and the derivatives of the function up to order n, because it is called an ODE of order n. So the maximum allowed derivative is the one with order n. So somehow this is the most general way to write down an ODE of order n, is any equation that it appears the independent variable, the function, and some of its derivatives are to order n. So this is the definition. And the second important definition is what is a solution of a differential equation? Well, a solution is a function that when you substitute it into the differential equation, it is satisfied. So for example, let's say I have a function that is called phi, and of course I need it to be differentiable as many times as the order of the differential equation. And when I plug in the equation, the function, it is satisfied, then we say that phi is a solution. This is very, very simple with an example. Let's say I have this very simple differential equation. Y prime t equals 3 times yt. Okay? So the unknown here is this function yt. This is the unknown. Okay? Now, what is a solution of this first order ODE? Well, a solution is a function that when it's plugged into the equation, it is satisfied. So let's try, for example, with a function phi, which is the exponential of 3t. If I take this function phi and I compute its first derivative, I will get the derivative of the exponential is itself times the derivative of the exponent, which in this case is 3. Now, when I use phi and phi prime and I plug them into the differential equation, I get phi prime t. Is it equal to 3 times phi? Let's check it out. Phi prime is 3 times the exponential of 3t. Is this equal to 3 times phi? Well, phi is the exponential of 3t. So yes, this equation is satisfied, of course, and we can guarantee that phi is a solution of this differential equation. So what you can see here is that it's very simple to check if a function is solution of a differential equation. It is as simple as substituting the function into the differential equation and checking if it is satisfied. Here you have another example you can try yourself at home. You have here a second order differential equation, second order because there is a second derivative here, and u is a function of time t. And now you can try at home to check whether this function cosinus of 4 times t is a solution of this differential equation. You should check it at home and see that yes, it is a solution. Okay. Now, there are two important concepts. The first one is the general solution, and the second one is what is called a particular solution. What we have seen up to now are particular solutions of a differential equation. A differential equation can have many different particular solutions. And when we have an expression that includes all the possible particular solutions, then we say that expression is the general solution. Let's see this with an example. I have this differential equation, okay? Now, I can try to check if this function is a particular solution. I can do that. And it's going to be very easy to check because y prime is going to be 2 times cosinus minus 3 times sinus. And then I need to compute the second derivative because this is a second order differential equation. And I will get minus 2 sinus minus 3 cosinus. And now I can substitute in the differential equation and I will get, okay, who is y prime prime x? It's minus 2 sinus minus 3 cosinus. And I'm trying to check whether this is equal or not to minus yx minus yx is this thing, is 2 times sinus plus 3 times cosinus. And we can see that it is true, yeah? So yes, this is a particular solution of my differential equation. Now, what I can see, and is very important, is the following. There are many different particular solutions, but there is one way, one expression that includes all the possible particular solutions. And this general solution is this, for this differential equation, is this one. Okay, so as you can see here, C1 and C2 are any real value numbers you want, okay? And you can check that for any value you want of C1 and C2, this is always a solution of the differential equation. If we have a second order differential equation, the general solution will always depend on 2 constants. If I have a first order differential equation, the general solution will depend on 1 constant. Here we can see how to compute the solution of ordinary differential equations using Maple. If you want to try it in Maple, I think is a good idea, but I will skip it in this lecture. Now, let me explain this idea of the general solution with a very simple first order differential equation like this one. In fact, we know how to solve this differential equation because it says that y prime is equal to 3t squared minus 4t. Now, if y prime is equal to this, y should be equal to the integral of 3t squared minus 4t, yeah? That's the definition of the primitive of function, yeah? So we know how to solve this first order ODE, and it is by solving this primitive, okay? Now remember that when we solve this integral, we get this, but I'm sure when you did calculus, you were told that there was something called the integration constant, yeah? Because when I compute the derivative of this function, what I will get is 3t squared minus 4t plus 0, because the derivative of a constant is 0. So the derivative of this function y, whatever value c has, the derivative is always the same. So basically, when I solve a first order ODE, I get this expression that depends on 1 constant, because it's a first order ODE, it depends on 1 constant. Now this is the general solution. This expression that depends on one constant is called the general solution. Here, if we want to find a particular solution, we need to impose an extra condition. We need to know something else. For example, here we decided to find a particular solution that at time 1 has a value of 4. Now, imposing that extra condition, we found a value for C, a specific value for C, that guarantees that this y with this value of C equals 5 is the particular solution that satisfies the differential equation and at the same time verifies this extra condition. Okay? Now, this is very important. Here you can see a plot of 4 different functions that all of them are a solution of the differential equation. All of them satisfy the differential equation. But only the red one satisfies the condition that when t equals 1, the value of the function is 4. The value of the function is 4. So that's the only one that satisfies the extra condition. So this is a very nice example that shows that when you have an ordinary differential equation, the solution of the ODE is a whole family of functions, a lot of different functions. They are a family because they are similar. The only difference between them is a constant, or 2 constants if it's a second order differential equation, 3 constants if it was a third order differential equation. Now I need some extra conditions to find the specific, a particular solution of the ODE. Now when you have an ODE plus the necessary extra conditions, we call this an initial value problem. And this is what engineers are interested in initial value problems. You have a specific problem with specific conditions. You want to find a particular solution. So normally, what you are normally interested is in a problem where you have your ODE, but also you have some extra conditions given. Now, these initial value problems, in general, depend on extra conditions. And if your initial value problem is an order n ODE, then you need n initial conditions in order to somehow be secure that you have one solution. We will talk about this in the next lecture on how secure we are that there is only one solution, okay? But this is needed, okay? We really need to have these n extra conditions. Finally, I would like to know that usually the independent variable is time, is called t. And that's why we call these extra conditions initial conditions, because we are thinking in time. So normally these extra conditions are given at the initial time 0. Think, for example, in the parachutist or the mass spring problem. The independent variable is time. So the extra conditions are given at the initial time of our experiment at time 0. So that's why they are called initial conditions. Here you have 2 examples of initial value problems. The first one is an example of a first order initial value problem. This first derivative here. This y also depends on t, okay? The unknown of this ODE, the unknown is yt. And we need one initial condition of the problem in order to have what we call an initial value problem, which is given by the ODE plus the initial conditions. The second example is a second order ODE. We have the maximum derivative here is 2, okay? So this is a second order differential equation. We need to add to the ODE 2 initial conditions in order to have what we call an initial value problem that we will see in the next lecture what conditions we need to guarantee that it has only one solution. But what is really needed, it's a necessary condition, is to have at least 2 initial conditions. We will see in the next lecture if we need something else. But this, to have the initial conditions, it's necessary to be able to guarantee that. And that's it for today. This is the end of this first lecture on the topic of differential equations. Bye bye. See you.